In linear algebra, most transformations distort space, stretching and shearing vectors into unrecognizable shapes. But a specific class of operators maintains a consistent geometric symmetry, behaving with a predictable balance regardless of the complexity of the space. This balance defines a normal operator. T commutes with its adjoint, T star. Because of this, any vector's magnitude under T equals its magnitude under T star. Therefore, if a vector scales by C under T, it scales by the complex conjugate, C bar, under the adjoint. Because T and T star share the same eigenvectors and shifted kernels, the inner product of vectors associated with different eigenvalues is forced to zero. The eigenvectors are effectively locked into an orthogonal state. Over complex numbers, this symmetry property guarantees that the entire space can be represented as a coordinate grid of these perpendicular eigenvectors. The operator organizes the space into a perfectly rigid structure. This organized grid is harder to maintain in real vector spaces, where we're restricted to real numbers and cannot always find real eigenvalues to define our vectors. The primary decomposition theorem breaks the normal operator into its basic real components. The space splits into 1D linear factors and 2D irreducible quadratic factors, which manifest as 2x2 rotation blocks. If you multiply this matrix by its transpose, it still satisfies the definition of a normal operator. The characteristic polynomial results in a sum of squares. Because of the b-squared term, there are no real roots or eigenvectors. Theorem 18 resolves this by showing that the real space decomposes into two distinct types of geometry: isolated 1D lines where vectors scale normally, and 2D planes where the operator acts as a rotation. Even when real algebra prevents the formation of a full eigenvector grid, the normal operator forces the transformation into these predictable orthogonal 2D planes. This order extends to shared invariance. Theorem 19 shows that any subspace that is invariant under the operator T is automatically invariant under its adjoint. The two transformations are geometrically tethered. This leads to the concept of unitary equivalence, the test for whether two operators that look different are actually performing the same geometric transformation. Proving this equivalence usually requires constructing a unitary matrix that maps one operator onto the other, a process that can be computationally exhaustive. For normal operators, Theorem 21 simplifies the requirement. To prove two normal operators are unitarily equivalent, you only need to show that they share the same characteristic polynomial. These three properties, commutativity, guaranteed orthogonality, and clean geometric decomposition, are all contained within that single polynomial. The characteristic polynomial is sufficient to define a normal operator's entire geometric reality. If the polynomials match, the operators are identical. To examine the formal proofs of these theorems, consult the source material in Hoffman and Kunze's linear algebra.